Well, first of all, let me use this opportunity to welcome you to IMSA. So an executive director. So I've been spending last year mainly brown nosing in different offices in Bulgarian ministry and foundations, trying to find funds to make this endeavor moving forward. And so what I'm going to tell you about is what I have done with some of my collaborators waiting in front of the doors in many different organizations, ministries, foundations, and so on. So since there are not so many obscurists present here, I notice, so I'll leave the coach theory approach, which can be used. So there is a pseudo anarchian category of the F bundles that probably serves well when you want to generalize this, especially look at different realizations like chaotic or chaotic. But since most of the people here are in singularity theory and mirror symmetry, I'll try to take this point of view. So probably in a couple, several weeks, bigger text is going to appear with the F bundle approach. See some of it there. All right. So the point of view that the program for today is to briefly remind you about some classical questions in birational geometry, then take the part of logical mirror symmetry that I'll need, and then of course tell you how to avoid anything to do with mirror symmetry, and just use the shadow of mirror symmetry as a guiding line. And then, so besides birational classical geometry, this will lead us to birational geometry, and also, so this in a way leads to birational geometry for quasi-projective varieties of like log funnels or funnels with some additional choices of devices in them. So you can do this as well. So, but so I've been thinking about this, as some of you know, for quite some time, and so it has been quite a struggle, and so I need to get some apostles in order to be able to at least advertise some of this work. Well, in any case, I'm sure at the end of the day I'll be crucified one way or another. But so this work was done together with Maxim Kuntsevich, who definitely played a leading role in the creation of the theory of atoms, Tony Pantev and Tony Yu on one side, and then with it was really product of IMSA when it comes to birational geometry. It's done with Maxim, of course, and Lino and Leonardo. So these are my apostles, no matter that they actually have Roman Latin names instead of Jewish ones. So now, I mean, in this area, I've been a little bit like, what is a good way to characterize this? So if you know a little bit about classical Russian music, there's pretty much corresponds to history of Russia. So there is this Boris Godunov, there's Kulashna, and there's Ivan Susanin, or more known to Die for the King. And so, of course, all these operas, in the same way as Italian operas, have very little to do with actual history. And they have changed through history. But one must say, of course, that no matter that how far they are from actual history, they are much closer than the history I've learned about Russia and Soviet Union in the 20th century. So, but the story of Ivan Susanin is as follows. So in the good old days, there was a big country named Rzeczpospolita, which was unifying Latvia, Litva, and Poland. And so it was dominating the region. So we're talking the end of 16th, the beginning of the 17th century. So after the Battle of Grunewald, initially they had quite a bit of influence. Yeah. But so, I mean, Russia was in a state of mutiny, and no one wanted to be the Tsar. And Mikhail Romanov was only 16 years old, and so he didn't realize how treacherous this Tsar position is, and so he agreed to be the Tsar. And immediately after that, Poles wanted to kill him, and according to the story, Ivan Susanin was a peasant who decided to offer his services to take them to Mikhail Romanov and the emperor and the Tsar. And instead of doing that, he actually took them to the swamps, and they all perished there. So in such a way, so Romanov was saved, and he started a dynasty that governed Russia for more than 300 years, from 1603 to 1917, when Nikolai II stepped down, eventually was killed. So, but my role here is mirror symmetry is very similar to Ivan Susanin. So I have been pushing mirror symmetry guys towards birational geometry, and of course we all ended up in the swamp. So the only difference is that I really wanted to help, not like Ivan Susanin, who really wanted to destroy the whole ordeal. So that's what my story will be all about. So, so I had some opportunities to learn variation with even, so I know it so badly that even, you know, so the main question of classical variational geometry is to relate projective varieties to the ones which understand best, and this is the ones which are variational to PM. They are called rational varieties, or in other words, they have field of rational functions as morphic to, let's say, over the complex numbers to see x1, xn, so mistake. So where n is the dimension of this variety x. So, of course, there have been a long way of different approaches to study this rationality or non-rationality, to be precise. So, I mean, in dimension one, so this first obstructions, they go back to Abel and Riemann, so who compute the homology of the elliptic curve and show that it's not rational. So now we will spend a significant time talking about the two-dimensional qubit today. It's a very telling example. But over the complex numbers, it was known to be rational, and this goes back to Italian school in geometry, I mean, so to Del Pezzo, so who knew that the cubic in P3 is blow up of between 6 points, let's say general position, smooth one. And then the three-dimensional cubic was really the claim to fame of Phillips. Doesn't seem to be around, but so what they did together with Clemens is they look at some also homological obstructions. This is so-called intermediate Jacobian, which is an abelian variety. So it should be Z here. So you embed the dual of the third homology group into the 2-1 homologies, and by integrating, and then this quotient is actually the abelian variety, which is called intermediate Jacobian of X. And it was well idea materialized by Philip and students to really answer the question when this intermediate Jacobian is not isomorphic to product of Jacobian curves. And so one of the first examples where this was carried out, this calculation and this analysis was carried out, was the example of three-dimensional cubic, which has a Hodge diamond like this one. And so as you can see, it looks very much like the blow up of a P3 in some corrections of in a genus 5 curve. But if you start analyzing this Jacobian, in fact, to be precise, the singularities of its theta divisor, you see that these singularities are in codimension 5. And if this was a Jacobian, the maximum codimension for the singularities of Jacobian, as Andreotti-Meyer theory tells us, is 4. So that's how Clemens and Griffiths concluded that this is not, I mean, the smooth three-dimensional cubic is not rational. So there are many different methods for studying non-rationality that were developed by different people. So of course, this was the method of intermediate Jacobian, which I already mentioned. So approximately at that time, a little bit more related to minimal model program method, studying the group of birational automorphisms, was developed by Skowski and Marin. So there were many other methods that were developed, and that's the method of degeneration by many people, Bozan, Chinto, Taro. I'm sure that I'm missing names. And of course, some people did combine the degeneration method with the method of intermediate Jacobian as well. So approximately at the time of intermediate Jacobian, Artin and Mountford introduced the method of Brouwer group, which of course later was combined with the degeneration method. And so another method which led to the proof of non-rationality of, another proof of non-rationality of three-dimensional quartic is the method of multiplier ideal shift. So, I haven't followed this closely, but so I think that it led to the proof of rational rigidity of hypersurface of degree n in Pn. So now some say up to n equal to 12, some say in general, and all this sort of. So, but that what we'll try to do here is look at different methods with the goal of putting some geometric metric structure on the more arrays. But we initially will do this with suggestions coming from mirror symmetry. But at the end of the day, of course, we'll introduce the theory of atoms in order to forfeit the information coming from mirror symmetry. But it's always good to keep any use of categories for that matter, but it's always to keep in mind the existence of this correspondence and meaning between A and B sides of mirror symmetry, and use the language of semi-orthogonal decompositions for categories to get good ideas. I'm sure that one day this will be developed properly. So now the first example we will try to approach by this new method is the example of four-dimensional cubic, generic one. And so let me just remind you that it has a Horst diamond as it's written here. So if you take this one out, this looks very much like a Horst diamond of a K3 surface. And so the whole point of the exercise will be to show that this cannot be a K3 surface, and the way to do that is in the lack of the theory of intermediate Jacobians is to introduce the theory of atoms. So now I need to briefly introduce some ideas from homological mirror symmetry. And so I mean the homological mirror symmetry is a correspondence between two categories. So so I will spend a bit of time on the case of dimension 2 and then go to dimension 3. But so basically we associate two categories to smooth projective variety. One is the category of coherent shifts, and then we have a Fukaya category. So now that's what we will be doing eventually. So associating two categories to the same varieties. So for us, the variety X, the funnels we will be studying, is going to be a smooth projective variety, and then also symplectic manifold. And so we will try to combine the classical theory of shifts on our manifold X with the theory on the same manifold. And so that's is going to lead us to a new type of chord structure, which eventually is going to be some kind of a pseudo Tanakian category due to other morphisms. But so this new enhanced non-commutative chord structures, which we'll be calling atoms, is the our goal. But the reason for looking at this combination of A and B side force structure and putting it together to form these atoms is the existence of this Landau-Ginzburg model, which actually is the mirror of our X. So we'll be working on one X eventually, but many of the things that we'll be trying to do are going to be suggested by existence of this mirror. And so that mirror, called Landau-Ginzburg model, is the best way to try to geometrize the these atom structures, which we are going to be using eventually. But once again, this is just a suggestion, and so I'll try to emphasize it on a couple of examples so that you see where this suggestion comes from. Eventually, so we'll try to record this in additional data coming from the quantum differential equation, just for the purpose of this talk. So there are many other additional structures that can be used here. So let's look at some examples which will give us opportunity to look at this. So first is the mirror symmetry for P2. So we have a derived category of P2, and that is generated by three exceptional objects, O of 1 and O of 2. And so mirror symmetry tells us that to this category associated to P2, we correspond to one category of Lagrangian cycles called Fukaya-Seidel category. And so that is a category defined on symplectic manifold C2 and with potential given by this function. So now the geometry of this picture is that so we have this function on C2 and it has three singular fibers at the third root of unity. So in fact, since Picard of P2 is equal to Z, so we can introduce a parameter here, let's say A. And so in fact, we have one parametric family of Landau-Ginzburg models, parameterized by H2 of P2. And so they give us one parametric family of Landau-Ginzburg model. And so this category here consists of so-called Lagrangian timbals, which are obtained as follows. So we take a base point, and so we choose paths on the base C. So this is the function W. And then so we take a vanishing cycle, which we homotopy following this path in the base. And so this timbal gives us a Lagrangian cycle in this category, which is corresponds to similarly we have other timbals here, and so that's how Morse-Cal mirror symmetry is proven in this case. So we have three exceptional objects and three timbals that correspond to them, and so you show that these two categories do are equivalent to each other. So now let's look at some things we know are birational to P2. For example, dB of P1 cross P1. So this, of course, has category generated by four exceptional objects. It's a product of the derived category of P1 and P1. And similarly, if you look at the mirror side, so we get a different kind of potential. And so, due to the fact that the Picard of P1 cross P1 is equal to 2, we have two parameters A and B. And so we have, in this case, as you can easily compute, a family of open elliptic curves, which has 4 singular fibers. And that's true for the case where A is not equal to B. But in the case of A equal to B, so we have actually two of these singular fibers coming together. So we have 3 singular fibers, but instead of two which have ordinary double points in each of them, we have one fiber where this elliptic curve degenerates to two rational curves which intersect in 2 points. So basically, this is the two-dimensional space of Landau-Ginzburg models. And then we have a divisor where these two points come together, if you like, to the singular fiber, give us another singular fiber. So now P2, of course, P1 cross P1 is birational to P2. And the way you move from one to another is by blowing up 2 points and then blow down the line that passes through them. And so we see that at the end of the day, if we do this, we create one additional, by blowing up 2 points and then blowing down one of them, we create one additional exceptional object. And then that's the difference. So we have one more additional object here, and then we have one more Lagrangian cycle here. And so what we want to observe is that these new things that we get via blow-ups, they don't talk to the previous one. So basically, creation of the new vanishing cycles are in addition to what we already have here. And so there is not too much interaction in general point. And of course, if the point is special, so there is a different picture. So now let me look at a little bit more involved example, and that will be the example of two-dimensional cubic. So that is a very classical example in birational geometry. So classical that even I took an exam on it with Manin a long time ago, and I didn't do very well, but I still remember something. So, and that is, let's see, first the cubic over complex numbers. So, as I said, we know that this is a blow-up of P2 in 3 points, therefore the corresponding derived category is what we have for P2, and then we have 6 other exceptional objects, which correspond to the 6 points we need to blow up. And not surprisingly, the corresponding Landau-Ginzburg model should look as we have 9 triples, and they indeed correspond to this exceptional objects. But the truth is a little bit more subtle here. So what's happening is that because the picard of the cubic is 7-dimensional, it's a Frank 7, so we have actually a huge family of Landau-Ginzburg models. And now, if you actually write the classical one, the one that comes from so-called Horry-Vapor theory, it is going to look like a family of elliptic curves. And then we have only two singular fibers. One of them is E6 tilde singularity. And one of them is ordinary double point. And so this is actually, if we take a very special Landau-Ginzburg model with parameters corresponding precisely to the canonical class. And of course, this is a very well-known singularity, you know this better than I do. And you can morsify it. And in fact, after morsifying it, you get to this Landau-Ginzburg model with 9 singular fibers. So we have this 7-dimensional so what's the name of singularity? Universal unfolding, and then in mirror symmetry that is called Frobenius manifold. And so somewhere here we have this point which actually has one E6 tilde singularity, but generic point looks like that. So for arbitrary parameters, you actually have full splitting of this Landau-Ginzburg model. So, and here for generic point, we see that we have these 6 new exceptional objects, this additional 6 points, which we have blown up, and they don't interact with what we already have. And so that's what we will be all talking about. So now we have a huge space of parameters, and so if the reason that we can bring it down to 9 singular points, 9 singular fibers, is because we can deform, we can morsify over this universally folding space. But what happens if we actually restrict in some smaller subspace? We cannot use the 7-dimensional space, but we are using something small. And that, of course, was noticed, not in this language, by Manin 60 years ago. And he studied rationality of the cubics over different fields. And so the field that he has chosen, I mean, of course, he looked at many cases, but was such a field such that the picard of this cubic is actually equal to Z2. So in other words, this is a conic bundle. So the cubic itself, so this is the cubic X, not the Landau-Ginzburg model, is a vibration of conics. And so you can actually compute the number of the singular fibers here. So this is the Euler formula. So there are 5. And so at that particular time, Manin introduced a criteria So let's say this is C. S is the divisor of is the discriminant. So in this case, we have 5 singular points. I'm sorry, it should be like that. Generic point is a conic, and then we have 5 degenerated conics. And so if you compute, what is it in this case? So the base is P1, so if you have 2 times the canonical curve of the canonical class of P1 is 2 points, minus 2 points. And then you have this discriminant divisor, which is 5 points, and so this is certainly O of 1, so it's not empty. And so this is where the famous 2ks plus 2kc plus s abstraction to rationality was introduced. There is a conjecture that was raised 30 years later by Skovsky that three-dimensional funnel is rational if and only if this quantity is not empty, with the exception of the example of three-dimensional cubic. I don't think it's proven, but many people, including Mori, Kukhlikov, Prokhorov, Conti, worked on that. So it's still open. But in dimension 3. But in dimension 2, so what that gives you is that if you have a field so that the Picard is equal to Z2, that cubic is not rational. And in fact, you can interpret that on the language of Landau-Ginzburg model. So you do restrict yourself to a subspace where the Picard is equal to 2. And then you don't have enough space to deform. So this E6 singular fiber stays unchanged, and so that's the reason we'll introduce later invariant why this two-dimensional cubics are not rational. So even in dimension 2, you can actually introduce quite a bit of new interesting mathematics when you actually look at questions of G non-rationality, and so we'll get back to this a little bit later. So now the idea is that in mirror symmetry, we get this Landau-Ginzburg model, which kind of keeps the exceptional divisors of the blow-up away. And if you can come up with some abstraction to begin with, under this birational transformation, this abstraction survives. So now, a very telling example is our favorite three-dimensional cubic. And so this example has been looked by many people, including Helge, Mark Gross, and me. And so, I mean, I give you the Landau-Ginzburg model. It's given by this potential, and it has 3 singular fibers. One is this open book configuration, which consists of 6 rational surfaces, and then you have 2 ordinary double points. But what we have observed is that you can read quite a bit about the Horst diamond by looking at the perversive of vanishing cycles associated with this Landau-Ginzburg model. And so the corresponding hypercohomology of the perversive of vanishing cycles are exactly I mean 5, 4, and 5, as it just means that you have rotated the Gauss diamond a little bit, and then you get the same number. So the information coming from the Landau-Ginzburg model mirrors indeed the information that you have from the coming from your initial variety. And so what we want to do is to remember the following, that so we have 3 singular fibers, and then so you have splitting of the Hodge diamond of your 3-dimensional cubic in 3 pieces. One is this big one, which looks like the Hodge diamond of genus 5 curves, and then 2 1-dimensional, which correspond to this singularity. So now what we want to do is to forget about the Landau-Ginzburg model and find some different, independent of the Landau-Ginzburg model way to think about it. And the way to do this is to look at the eigenvalues of the quantum multiplication by the C1 of Tx. And it is known that they precisely correspond to these points that we have as critical values of the corresponding function. So we forget about the Landau-Ginzburg model, and so what we want to remember is this eigenvalues of the quantum multiplication by C1 of T of x, where x is our function. So what do we get here? So I mean, in the case of 2-dimensional cubic, which I worked out for you, so we have different points in this modular spaces of Landau-Ginzburg models, and over each of these points, so we have this lambda 1 to lambda 9, which are the eigenvalues of the quantum multiplication by C1 of Tx. And so at this point here, so we have actually only 2 of them. And so we can think of this as a Frobenius manifold as having over each of these points the homology of the cubic, which has different splittings. So in generic points, we have 9 pieces, but in this very special one, we have only 2 pieces. So a different way to think about this, that we have a spectral covering over the H2 of the cubic mod tensor C, and then for generic point, we have 9 points which cover this. But for very special points, they actually become less than 9, 2 in this case. So we have some very serious ramification, and then we have this discriminant where the eigenvalues of this quantum multiplication by C come together. So this is the ramification divisor. So of course, most of the arguments we'll be using will be for generic point. This is where the invariants are going to be built. But if you want to study things when you have group actions, in which the algebraic cycles are abstracted either by this group action or by some additional data, we will restrict ourselves to some of this abstracted Landau-Ginzburg model, and so we'll look at what's happening in these cases. So the invariant that we want to remember from mirror symmetry and then forget about it is this Picard or if you like, all algebraic cycles in higher dimensions, tensor C. And then this spectral coloring consisting of the eigenvalue of the multiplication by the canonical part. So, this splitting, so this local eigenvalues, give a splitting of the homology of our variety. And that's the invariant that we want to remember. So over this space of algebraic cycles, we have a vibration of the homology of our variety in different points. It's different. And then this splitting is recorded by this spectral coloring that corresponds to the eigenvalues of the quantum multiplication by C1. So now these are the data that we want to remember and claim that they are operational invariant. So this is the only thing that you remember from mirror symmetry. Where do they count them? But this is all data which can be completely determined by the quantum differential equation, or if you like, by the Braun-Witten theory. So now I must say that I'm just giving you the simple example here. So simple interpretation, which is with the very simple idea of in mind. Trying to get to the four-dimensional generic four-dimensional cubic as quickly as possible. But of course, these homologies, they have corresponding to each point, they have this structure associated with them. So you can enhance this. And so look at this homologies in addition with this structure. And so there's something which is called gamma conjecture, but up to dimension 2, it's clear. And so then this gives you a stronger invariant, including the image of the K theory. And that is something that you will be able to use if you study different type of questions going beyond the generic four-dimensional theory. For now, we are dealing with the generic point. Any questions before we move to yes?
Can you describe the endomorphism algebra of this exceptional production?
Yes, that's how mirror symmetry is proven. So you prove that this endomorphism algebra is isomorphic.
So for this specific case, where's the corresponding figure?
Yeah. So if you look at the paper that, so in the case of the Opezzo, as I wrote with Oru and Orlov long time ago. So take it in invenciones, and so that's exactly how mirror symmetry for the Opezzo surfaces. So you show that this algebra is the same. Yes?
So at least conjecturally, do you obtain a non-commutative variation of what structure if you vary the point there?
It's not conjectural. It's just a Higgs bundle given by the B module given by the quantum multiplication. It's not conjecture.
But you obtain something that varies with the same x.
Yeah. So you have the Frobenius manifold and you have a variation on it. So now, it does satisfy Griffith's transversality. So now you can do this in the quasi-projective case, but you need to develop a little bit Braun-Witten theory. But that's something that we do now with Max, Leonardo, and Trino, and so you get quite a bit of abstractions for in the quasi-projective case, and so the extensions of this. So the combination of this K theory abstractions in connection with the extension gives you new abstractions in this case.
What exactly is the cohomology of F is here?
Meaning of the perversive of vanishing cycle.
F is the perversion.
Yeah, so this is the, if you go to this C2 with the function, there's a perversive of vanishing cycles, and this homology are the hyperhomology associated with it. Other questions?
The eigenvalues of the monodromy, do they also correspond to something else?
I mean, of the monodromy around each fiber?
Yeah.
Yes, we'll talk about this in a second. I mean, so in any case, I'll give you the answer now. So from point of view of analysis, they correspond to the asymptotics of the function differential equation. From the point of view of algebra, these are the coefficients of the logical modular forms associated with these vibrations of Labial. But they will appear later in our considerations today. Other questions? Yeah, all right. So, already here, if you accept this splitting, if you accept that this splitting is a birational invariant, which we'll talk about a little bit, you already get the whole theory of intermediate Jacobian replaced by Gram calculation. So in the case of three-dimensional cubic, you can easily notice that the self-functor acting on the cohomology of this cubic has the property that so this is acting on this piece, has the property that it feeds the self-functor in degree 3, it's equal to shift by 5. And so this cannot be a self-functor associated with the whole diamond of any Riemann surface. So that's already tells you that if you have this splitting as a birational invariant, this three-dimensional funnel cannot be rational. And that's true in all of these classical examples of funnels that have been studied 50 years ago. So the self-functor can never be a self-functor of a Riemann surface. And if you assume this being a birational invariant, so then you'll get that these three-dimensional funnels cannot be rational. So, all right, so let's see what where do we stand then. So we have this vibration of coming from the Landau-Gisburg model, which we want to forget. And then, so we want to use this quantum D module in order to get the position of these singular fibers. And then, as I said, the base, so the whole thing should be considered together, although for our purposes, for now, we are only interested in the generic point. And so we just need to get the canonicity of this splitting in order to get that this is a birational invariant. So now I just want to point out before we switch gears that there is one other thing that you can notice here. So these Landau-Gisburg models, there are tricks that you can play with them. So in particular, you can degenerate them. And so you can degenerate this singular fibers, or if you like semi-orthogonal decomposition, in pieces. And that actually gives you additional Hodge type of question that you can pose. Are these extensions of Landau-Gisburg models, or in the language of differential of derived categories, are these gluings of derived category giving you additional abstraction? And the answer is yes, they do. And so other things that you can do is take some fibers out. And so that corresponds in the classical birational geometry of singularities of pairs. And so in this case, we can take combination of fibers out and then study what's happening there. As soon as you have defined volume element, I mean, so the A side is going to work, and then you can pose all the questions about this birational geometry of the pairs, triples, and so on and so on, and then you will have some extensions that will give you opportunity to do this. Of course, you need to know enough Foucault Seidel-Rapp theory, or if you like, enough Gromov-Witten theory of the local Abbiaus in order to develop these things, but you are in favorable situation and this can be done. All right, so this is our savior, the quantum differential equation. So instead of looking at the Landau-Ginzburg model, so we forget about them, and we just look at the data coming from this quantum differential equation. So let's stay with our favorite three-dimensional funnel, that is the three-dimensional cubic. And let me just tell you what this K and G are in this case. So for the three-dimensional cubic, so this is the, so you have 4 algebraic cycle associated with the three-dimensional cubic. So that is the base of the Frobenius manifold in this case. And then on this algebraic cycle comes the quantum multiplication by K, is given by this matrix. And then the matrix G is
How do you obtain these cycles? Is Mendeleev's?
sorry?
How do you obtain the cycles on the Frobenius map?
So this is H00, this is H33. So I mean, I have 4 algebraic cycles. That's an obvious thing. So now, this is the theorem which makes our splitting of birational invariant, which is very much based on the work of Iritani. So in any case, what the claim is that so for generic point of the Frobenius manifold, so we use the eigenvalues of this quantum differential equation, so the singularities of this D module, and then that gives you a canonical modulo contributions of codimension 2 and higher subvarieties of our de Rham homologies, which happen to be birational invariants. So we think of them as de Rham pieces, but also which are fixed under the action of the Mumford Tate group, but also as a non-commutative core structures associated with this A-side category that we have on our subjective manifold. So we have this Z2-folded polarized core structures on H. And so each of these pieces, taught as a de Rham and taught as a non-commutative core structure, are called elementary pieces. And so the important thing is that so 2 varieties are birational if and only if this splitting is the same modulo contributions of subvarieties of codimension 2 and higher, and of course of the reaction of the symmetry group, which I forgot to put here. So that is the statement that makes this birational invariant. And so now the proof of this theorem is strongly based on a work of Iritani. So now we need to give a names to these pieces, elementary pieces of the splitting, and we'll call them atoms. And so now I was very much against this name, but actually, obviously, it's not me who decides. But but nowadays, with additional data of these divisors and so on, so something which is like a Mendeleev table that appears. So it's a very good name, post factum. So some of this will be discussed today. So so we have this base, which is this algebraic cycles, Hodge class.
One second, should we take a 5-minute break and come back for another hour?
I mean, it's you're the.
So,
I mean, I can do it. I can only. I need to leave at 11 because I have a meeting where I need to do a little bit of begging for some funds for him. But I mean, okay, let's say 2 minutes, 2-3 minutes break.
or we can just go on. Everyone needs to go to the bathroom? Let's go on.
All right.
Take a little
So,
break, half an hour.
Now, I mean, so the base of this Frobenius manifold are the algebraic, or if you like, Hodge cycles. Wrong. So in any case, so this atoms are going to be basically for us this connected components of the homology or this Frobenius manifolds associated with the Hodge cycles corresponding to splitting associated with the generic point of this Frobenius manifold, which is this space of the Hodge cycles. So the local behavior, local component associated with generic point of the spectral coloring is something that we will call an atom. So as I said, it is fixed under the action of the Mumford-Tate group. So this H lambda corresponding to generic point of the base are called atoms. So now I just want to point out it's a kind of took it off, but so one of the main reasons why I mean personally I was stuck with this for so many years was that it's not only, but it's a central one, is the existence of some phenomena which is called phantoms. So these are categories which have trivial homologies and trivial K theories, but actually exist. And so the main problem for me was that these atoms could appear in these semi-orthogonal decompositions, and they cannot be seen as a homology. So the point here is that when it comes to the splitting, so the atoms only generically appear in the case when we have surfaces of mixed types. I mean, certainly elliptic surfaces and surfaces of general type. But in this particular case, although we can go further in terms of doing semi-orthogonal decompositions, the one semi-orthogonal decomposition, or if like splitting of atoms, which comes from the Gromov-Witten theory associated with these surfaces, consists of one point. So the atom associated to a surface of general type, surface consists of only one point. And that was an essential part of overcoming issues related to existence of atoms. So now, existence of phantoms. So we can put some equivalences of these atoms. So we consider the set of all atoms associated with certain manifold modulo the group action isomorphisms of X. And so the theorem of Eritani, which is a certain blow-up formula for the quantum homology, tells us that if we consider all this, I didn't introduce the notion of F bundles, but these vibrations of homology of the Frobenius manifold for these two, for a manifold X and submanifold in it Z, which we want to blow up. So in fact, locally, these vibrations look like a product. I mean, so the one associated with the blow up of X and Z is locally a product of the ones associated with X and Z. So these vibrations locally, they look as products when we blow up. And so this gives you in a way nature of filtration. And so that is a major, this observation of this locally they look like a product is a major point in the proof of the statement in the previous theorem. So, I mean, this observation allows us to formulate that following approach to abstraction to rationalities. So, if one of these splittings, homology, one of these atoms, does not correspond to a atom, or if you like, chord structure of a manifold of four dimension 2 and higher, then this is an abstraction to rationality. So in the same way as we have started with this intermediate Jacobians, so I mean, if one is not isomorphic to product of curves, then this is not rational, as we said. And this is the example of three-dimensional cubic. So here, if we have an atom that cannot be associated with a subvariety of codimension 2 and higher, then this is an abstraction to rationality. Except that this approach works in higher dimensions, and of course it can be enhanced in many additional ways, as I'm going to show. So now, now we are already have enough to address the question that I posed of the generic four-dimensional cubic. And so now, in the case of four-dimensional cubic, so we have the following splitting of its homology. In fact, to say put it differently, we have four atoms. One that looks like this piece, and then three others that are just of dimension 1. So we have four eigenvalues of the quantum multiplication by C1 of T of X, and the 1 over 0 correspond to this piece. Now, there are many ways to approach this, and so, but the fastest and the easiest one is to notice that this atom actually has only two algebraic cycles in it. And all algebraic surfaces, for obvious reasons, have at least three algebraic cycles. So this atom cannot be corresponding to a algebraic surface. So that gives you an abstraction to rationality of generic, once again, generic four-dimensional cubic. So you actually can do more. So you can consider questions of non-rationality for some non-generic cubics. For example, cubics containing a plane. And so in this case, you always, you can also show that generic cubic containing a plane is not rational. But you need to enhance this theory considering this structure coming from the so-called gamma conjecture in this case. And in this particular case, you do show that cubic containing a four-dimensional cubic with a plane, generic one, is not rational due to the fact that the intersection form associated with the atom cannot be an intersection form on an algebraic surface. So with these methods, you can take other funnels, I mean, like so-called Pushel fourfold, the intersection of three quadrics in P7. It's a very interesting example, actually, where you can really degenerate and still get no rationality, this time based on a combination of K-theory and extension classes. So now there is this question that conjecture which was posed by Kuznetsov, saying that cubic is rational if and only if contains K3 in its algebraic K3 surface in its semi-orthogonal decomposition. So I must admit that I always believed that. But some recent developments based on this splitting of the Landau-Ginzburg models and good categories make me doubt this statement, and maybe there are interesting examples of four-dimensional cubics which have K3s. They are semi-orthogonal decomposition, but they are still not rational. So this for me, jury is out. That's quite possible. So in other words, could be that there are deeper invariants than just these atoms, which are basically connected with the extensions of these atoms, and and then you will have all of these atoms corresponding to algebraic varieties, but the extensions actually are the ones that give way to find no rationality. So now I'll say a little bit more about this later. So there is a very good candidate for these extensions, and that is the elliptic genus that allows you to do that. And so I'll mention this a little bit later. Any questions?
Yeah, the definition of atoms was a bit too fast for me. For example, in this case, how does one, can you?
Which case?
The one that
The two-dimensional cubic?
Yeah.
So I mean, in this case, so we have only second homologies, and so you have Z9 to be. Oh, sorry, I lied to you. So it's Z7. That is the second homology group, and then so if you so this is the base of this Frobenius manifold, and for generic point you have a splitting of H0 plus H2 plus H4. So this is a nine-dimensional space, and so for generic point, I mean, so I have so because of this L1 to L9, so I have that this H is direct sum of these 9 one-dimensional spaces. And so over generic point, we have this 9-sheeted spectral covering.
What is mu in this case? It was a mu definition.
Mu is 9 in this case. I mean, so it's the number of the splittings in the for generic point.
How does one see that from the operator? So the operator.
Yeah, operator is going to have 9 eigenvalues. I mean, so in this case. I mean, so this is for three-dimensional cubic. For two-dimensional, you have 9 to 1 matrix, and sorry, 9 by 9 matrix, and that is going to, sorry, I apologize. For three-dimensional, you're going to have 7 by 7 matrix, and then it has 9 singular points.
So the maximum value of the spectrum is not an eigenvalue. It's
I mean, those spectrums are the critical values of the operator, and so there is a spectral covering, and so that is given by the solutions by the critical values of the quantum multiplication. And so there is a base which consists only of the Hodge cycles. So these are different. So that's and the difference is even more obvious if you start restricting to sub sets of this Rubinus manifold where these eigenvalues started coming together. So in a way, this difference is the main name, is the name of the game. So, and I'll work out one example to emphasize this more less strict. Yes.
So it's in the previous picture, so in the vanishing cycle, it's already separated. So that means that the linking diagrams are not connected or something like that.
Yeah. I mean, so in this case that is there, you have 9 A1s. Yes. So you have this very singular A6 tilde.
Yeah,
So most of our generic point, you have 9 A1s.
Yeah, I understand, but even when you combine them, the intersection force because so much. So that means that somehow they have different blocks when they don't, even when you move them, they don't intersect. So the linking diagrams are connected or not connected. That's the point.
Well, I mean, so the point is that you reduce this space to from 7. I mean, so generic point, of course, you have the splitting. I mean, that's in the singularity theory. You have multiplication. But if you don't allow to,
but is those you bring in the very same fit space?
Yes.
And then
But if you take this
yes.
this point out, you cannot do this. Therefore, they stay of higher ranks. And so now I will introduce for you invariant that you understand way better than I do in the next slide. And that, of course, is the spectrum. And then once you introduce the spectrum, so this question is solved. But this is not the spectrum of the D module, but the so singularity theory, you have better understanding how is this called. So I'll use all names that are available to me. Arnold, Saito, Stimling, spectrum, whatever you want to call it. So yeah, all right. So once again, I mean, so I have chosen this approach with referring to Landau-Ginzburg model. I mean, this could be completely avoided, and then you generically introduce this theory of F bundles. That's the way the text is written. But first of all, that spares you quite a bit of intuition, and then historically things were developed differently. But in order to see the other applications, like to a quasi-projective case with group actions and so on, I mean, so this keeping the connection with the Landau-Ginzburg model is quite useful. So all right, so now we go a little bit further and to answer the questions that were posed by Nero and by Andras. So you could milk much more information from this quantum differential equation, and that is to look deeper at it and not only at the look at the solutions, but at their asymptotics as well. And so that corresponds to a mirror seriality statement, which I mean, I was discussing, but will appear in the joint work with Uru and Kunsevich, that if you look at the Landau-Ginzburg model and you look at the corresponding Arnold side of Steinberg spectrum associated with the deepest singularity, then these numbers of the spectrum that you compute here, they correspond to the asymptotics of the quantum differential equations, but restricted to this biggest atom, which you can always do in the case of Fano manifold. So once again, the classical Arnold side to Steinberg spectrum associated with the Landau-Ginzburg model corresponds to the eigenvalues of the, sorry, I apologize, asymptotics of the quantum differential equation restricted to this biggest atom. So now from this perspective, this question for non-rationality of the cubic, two-dimensional cubic that has pK equal to 2 can be seen as follows. I mean, so you cannot further degenerate this thing. And the Arnold side of Steinberg spectrum for this E6 singularity is 5 something. I forgot, 5 sevenths or something like that. It's certainly bigger than 0. And A1 has spectrum equal to 0. And so I have a theorem here which tells us for hypersurface of degree P, 3 in this case, if delta, which can be computed by this number, is bigger than 0 in this case, so I have 2, and then I have 2, the cubic is in P3, so this n needs to be 4, so 4 minus 3. N is the dimension of the number of the variable of the projective space where this hypersurface is variable. So in this case, when for two-dimensional cubic is 4. You have 4 variables in P3. So so you get so I mean so you get 4 minus 3, so 2 minus 2 is 0. So strangely enough, generic two-dimensional cubic is all the complex numbers is rational. And that's exactly correspond to the fact that we have these 9 A1s, which have their spectrum equal to 0. But if you don't look at the generic form here, you look at a special point. I mean, the Arnold cytostymbric spectrum is actually a number bigger than 0. And that's why you restrict cubics where pK is equal to 2. And you get fields where the Galois group doesn't allow you to move further. So these cubics are actually not rational as the spectrum suggests. So you can.
Excuse me, I didn't pay attention. What is capital N?
So we have a hypersurface of degree n in Pn minus 1. N is the number of the variables in the weighted in the projective space where this is a hypersurface.
So dimension of X is N minus 1.
Yes. No, dimension of X is n minus 2. So this is the number of variables in the projective space in which we are embedded. So in the case of, so let's do the example of three-dimensional cubic. So for the three-dimensional cubic, so dimension is 3. So 2 times n is, so the cubic is three-dimensional, so we are in P4, we have 5 variables. So we have n minus 3 over 3. So 3 minus 4/3, so we have 5/3, and that 5/3 is certainly bigger than 1. That's a different way to prove that three-dimensional cubic is not rational. So observe that in dimension 4 this doesn't work. So we get this number to be equal to 4. So, and that's why this, this number to be equal to 2. That's why this criteria doesn't work for three-dimensional cubic, but a different one with algebraic cycles does work in this case.
And what was the intuition, the mirror intuition, that is, if the minimal spectral number is bigger than 0, why should that?
If the, so I mean, yeah, so that's a very good point actually. But so now this is not the mirror intuition. So in physics, before mirror symmetry started, there was another type, and that was called conformal field theory. And so in conformal field theory, there's a notion which is called R charges, which are very hard to compute. So if you actually can compute it for conformal field theory, you buy a ticket for Stockholm. But in the case when these conformal field theories are massive, namely they correspond to geometry, you can use geometry to compute these numbers. These are charges, and they happen to be connected with geometric data associated with this conformal field theory. So funny enough, when spectrum of singularities and conformal field theory, they were developed in the same city, and maybe even in Moscow, and people from both groups attended each other at seminars, but they didn't make the connection. It was actually made by Buffer before even mirror symmetry type started in joint work with Chakotay and Wisdom. So where he actually, in the case of very simple singularities, definitely connects the following three things. R charges for the conformal field theory, the singularity spectrum for AN singularities, and asymptotics of the corresponding differential equation in this case, which is some Japanese name, I forgot. And so, I mean, of course, I mean, it's a physics speculation, but it turns out to be correct. So these three things are connected. And now, so what we are saying here is that there is a conformal field theory associated with this sigma model. And so now, one thing that was noticed by them, but there is something which is called the classical limit. And in the classical limit, so this R charges become nothing else but dimension of our manifold. And so if you have some variety of general type, the corresponding, if we put delta, is going to be just equal to the dimension of the manifold. And now, if you're at this point and you have for your theory number which is bigger than the dimension, so you on the boundary know that your variety cannot be algebraic variety because the spectrum is bigger than what you are going to get from the dimension. But now you need to go inside for generic point and show that this inequality continues to be happening. But so here comes a genius theorem from a physicist Its name is homological, and it's called in physics homological C theorem, which tells you that if you go inside, this number can only go up. So if it's bigger on the boundary than the dimension, so it's going to stay bigger if you go inside in this moduli space of conformal fluid theory. In this case, Ludmil's manifolds. And so you need to, so the in the mathematics, this how is this called? Semi-continuity theorem was proven by, you have some proof, but you have some proof later. Okay, fine.
Yes.
So in any case, Varchenko and Stimbrink, and so that's the analog of the homological theorem, and then Max found really easy proof of this for semi-continuity, and that applies to all these situations. So this is kind of a result of all this. So, but indeed, so it's important that for if you consider conformal field theory, which are based on manifolds of general type, well, also, but so this biggest number of the spectrum is equal to their dimension. And so that's what we are trying to ask here. If we have this number which is equal to 5/3 here, and it's bigger than 1, so we want to compare this to a Riemann surface. So for Riemann surface, a conformal field theory associated with Riemann surface, this number is 1. And so on the boundary, it's 1 here, and we all computed that it's equal to 5/3. But also by this homological theorem, we know that we go inside, this stays only goes up. So for generic point, and that's what we want, this difference is going to stay bigger. Right? So 5/3 is bigger than 1 here, it's going to stay bigger inside, and that's how we conclude that generic cubic is not rational.
Dimension is not important in comparing with the rational curve. It's not
I mean, of course, semi-continuity, I mean, it doesn't matter how you get there. It's just inequality. In any case, so now, I mean, of course, I'm just touching the surface. I mean, so there are other arc charges and then other asymptotics. So this can be explored as well. So it becomes even more interesting, but technically harder to prove in the quasi-projective case where all these things, I mean, so of course, I mean, so there is a connection, as we know from Nero's work between monodromy and this number. So monodromy remains monodromy in the quasi-projective case as well. I mean, just there will be some defects that you need to take care of. And then it's even more interesting in the case when you have group actions. And so I would like to talk a little bit about that. So now, I must say that for me, the interesting question has been always, if you have just Landau-Ginzburg models, can you have Landau-Ginzburg models which look very much like the Landau-Ginzburg models for rational varieties, but there is additional invariant that is hidden in the geometry of the Landau-Ginzburg model, which serves an abstraction to rationality. So now,
one more question.
Yes.
So in the case the mirror exists, the number delta that you put on the board, does that correspond to the minimal spectral number?
yeah. I mean, so take the minimal spectral number and multiply it by -2. That's what delta is. It's related. I mean, it's for all of them. Yeah, okay. So, I mean, as I said, for me, I mean, the interesting question is there additional geometric information hidden in the Navier-Stokes model, which is not only the atom, but how these atoms are glued together, like extensions of the corresponding obstructions. So, I mean, this is a very deep question amounting to studying, I mean, all these gluing of semi-orthogonal decompositions in which Russian schools so overall can develop quite a different techniques. But so still, and I'm sure that to all now you'll be doing this invariants based on categories and stability conditions. And so if you want to do four structures, and so you want to, which is the legal approach at the moment, so you want to stay with corresponding atoms with the horse structures. So now, but and I just wanted to see how this, what are these things that could obstruct rationality by just looking in the Landau-Ginzburg model away from the singular fibers. And so intermediate step, a very good one, is to actually look at G birational geometry. So now I must say that this notion was introduced a long time ago. I mean, after by many schools, the French school, the Russian school, of which I learned nothing. So in any case, so here's a question that I learned in Moscow around 1983. By Skovsky. And so it is a following question. We take a hypersurface of degree 1111 in P1 cross P1 cross P1 cross P1. So it is a nice funnel manifold move. And so over the complex numbers, this is actually a blow up of P1 cross P1 cross P1 in elliptic curve. So it's very rational. I mean, this is just blowing up of P1 cross P1 cross P1. And so now the question that was posed by Skovsky, I mean, so let's say that we consider this funnel over different field. Let's say a field with Galois group Z4, which acts transitively on these four P1s, or any transitive group acting on this for that method. And so I have something which is rational over the complex numbers, just like the two-dimensional cubic. And then, so I want to study the rationality of this with some group action, G equal to Z4. So what does this mean from the point of view of variational geometry? So we have minimal model program, and we have these Mori rays. Instead of looking at all Mori rays, we look only at few of them who are G equivariant. So we restrict the number of birational transformations that we are looking at. So as I said, over the complex numbers, this is blow up of P1 cross P1 cross P1 in an elliptic curve. And the question that we are looking at, can this be done Z4 equivariant? Can this blow up be done Z4 equivariant? So at that time, that was not known. And I think that until very recently was known not for all, but for some of this. And so I'll propose several different ways to look at this, to answer this question, and of course many others. So now let's look at the I'll just directly give you a corresponding splitting on atoms. So, so I have this elliptic curve, and then I have 8 others critical values, and they correspond to the fact that I mean, like H2 of P1 is 2, and so I have 2 cross 2 cross 2, 8 additional Bragg cycles. Or if you like, I have 8 additional singular fibers. Of course, this happens to be the same here, but because derived category of P1 cross P1 cross P1 is a product of 3 derived categories. So I have additional atoms of the simplest type, just a point. So that's the splitting of atoms of my funnel, which consists of over the complex numbers, which consists of 9 pieces. So this and so this piece here corresponds to the elliptic curve that we blow up in P1 cross P1, and there is no obstruction of doing this over the complex numbers. So now, what we want to do is to look at this splitting G equivariant. Namely, let's do this from the point of view of action of this group. Well, if carefully do that, you will see that this splitting of atoms actually in this case changes, and it's G2, Z4 atoms, so equivariant Z4 atoms. And so equivariantly, we have the following splitting. So let's see if this is correct. Like that. So instead of 9 critical values, so 9 atoms, we have only 3 of them, which are Z4 equivariant. So it's rather clear that you need to have one permutation module, this 4, one trivial, and then you have this piece. Which means that if I look at this, in this particular case, huge so 10-dimensional Frobenius manifold, I mean, if you restrict myself to the Z4 equivariant one, so I only have 3 atoms, so it's 9-dimensional, 9-sheeted spectral coloring. But if I restrict myself to the Z4 equivariant one, it becomes 3-sheeted coloring. So I have this ramification divisor. So I have splitting of these 3 on these 3 atoms, and of course you can show that there is no further splitting. So this piece doesn't look at all as a course diameter of a Riemann surface. So, and then that tells you that this cannot be a blow up J equivariantly, or like Z4 equivariantly, of P1 plus P1 plus P1 in an elliptic curve. So this is an abstraction to this coming from the fact that you have this very strange atom that corresponds to one-dimensional manifold. Of course, there are many generalizations of this very simple but still unknown, now known example. But now we want to go further. So this is all on the atom side. But not so long ago, Katzarkov came with a different invariant, totally unrelated to the theory of atoms, and that was so-called symbol obstructions. So this was done in a work with Chinkel and Pestu, and then many additional examples were worked out by Chinkel and other people. But so what we would like to do is to basically do the following thing. So the theory of Burnside groups, which is the group of defined as follows. So you take all, so it's a theory of symbols. So you take your varieties on which you have group action. And you have fixed points under this group action. So fixed sets, they form subvarieties, points, whatever they are. And so there is a theory of birational geometry associated with these fixed points. And then there's also a theory of atoms associated with these varieties, which is this Landau-Ginzburg model. So there are some examples which you can show that they are not G-rational using this theory of Katzarkov, namely the way it's defined. You take a ring, the generators of which are the local behavior of your fixed points, and then they form a ring, and you mod out by all birational relations, and so that's what your Burnside ring is. And you have this theory of atoms, which I just described for you. And so what we want to do is to obtain a new invariant which combine these two Burnside invariant and the atom type of invariant, which we just described, to get new abstractions to G non-rationality. So, and in fact, the question is, we know some examples which are given by the atoms. We know some examples which are given by this Burnside abstraction. Can there be examples which can be only distinguished by cannot be distinguished by the symbol, by this Burnside abstraction, by the atoms. But if you can construct a new invariant based on both, you get new abstraction to rationality. And what I'll do is briefly tell you about this type of invariant, which gives you an approach to this breaking of the Landau-Ginzburg models without any group action. I think it goes very far, so I'll try to do this in the next 10 minutes. So eventually, then, this ends up with four modular forms, but the initial invariant is as follows. So we are going to bring a new type of Burnside ring. So the first generators are going to be this type of atoms, G equivariant atoms. And the second are going to be, so here I write it as a categories with G action. So of course that's the right way to think about it, but the legal way for now is just atoms with G action. And then the second is this symbols that were defined by Kontsevich. So these are the fixed point sets under the group action with the corresponding behavior of the normal boundaries. So these form one Vic ring with relations, and we are going to define an invariant associated with this ring, which is computed as follows. So we combine two things. So first, the pieces in the semi-orthogonal decompositions, that's the right way to think about this, but actually these are G invariant atoms. And then the other characteristic of the coming from the things which are fixed under the action. So this is just a combination of the numbers coming from the atoms and of the fixed points. So both of them, the fixed points and the atoms, come into the formula. And so if this number happens to be non-zero, then this is an abstraction to G rationality of the corresponding manifold with this G action. So once again, so these are data coming from the Euler characteristic of the fixed point sets and the pieces which in the atom splitting, which are G equivariant. And so if this number happens to be non-zero, then this manifold is not G rational. So since so there are two interesting examples that I want to point out. One of them is the two-dimensional quadric, the rational manifold over the complex numbers, but with the action of the H3 group, which acts in the following way. So if you compute this number for this three-dimensional quadric and the S3 action, you get number which is non-zero, and that is certainly an abstraction to S3 rationality of this two-dimensional quadric. It's a very classical question posed by Miskovsky and Dolgachov a long time ago. And let me just return to the example that I already pointed out to you. And so that is this 1, with the Z2 action. So Z4 was there with the atoms. So let's consider the same manifold but with Z2 action. So still unknown until this technology was developed. So if I have this block of Q1 plus Q1 plus Q1 in a elliptic curve, so what we are asking, can this be done Z2 equivariant? And the invariant that I have just introduced, which tells you the combination of Carnot combination of this fixed point sets of symbols and the atoms, tells you that this cannot be rational, G-rational, it's two-rational because of the fact that this number is equal to zero, indeed. So with this fixed point sets, in this case, is just two rational curves, delta and A, which intersect in 2 points. So that has Euler characteristic 4. And then the fixed point sets of the Euler characteristic of the fixed point sets is, what is it? 4. So we have 2 coming from the fixed point sense and 4 coming from the atom, so it's 2 minus 4, it's equal to minus 2, so it's not 0. So then that's why you get that this P1 plus P1 plus P1 will not be an elliptic curve, it cannot be Z2 rational. So now, of course, this is just the simplest type of invariance you can put. I mean, so first you say it's 0, then it's the Euler characteristic, but then you can get a little bit more serious. And there are some topological modular form with elliptic genus, which behave very well under blow-ups. It's almost like invariant, as proven by Serge Sushanin a long time ago at the development of all these modular forms, like elliptic genus. And so, indeed, in this case, you could employ the elliptic genus to study this question of gluing of Landau-Ginzburg models, and when this gluing gives you additional abstractions to rationality, which don't come from the atoms themselves, but from their gluings. And so just to point out that elliptic genus actually is connected with this number of the spectrum that we have mentioned. And so basically what's happening here is that you have this big, very singular fiber, and you put some additional manifold over which you want to do the splitting. And then eventually the calculation comes to computing the elliptic genus of this combination of atoms, and then the invariants are exactly this spectra, the monodromy, which comes from this pair or triples of atoms that you want to study. And so it's again just a refinement of the procedure that I already mentioned, but gives you new instructions to rationality. So I have to stop here because I need to go and beg the provost for some more money. Any questions? Yes?
Maybe it's not exactly related with it, but about that model, that if you have a G action, yes, then it's going to have a falsification of the vanishing cycle. So
I mean, very good. I mean, so indeed, that's a very good question. In fact, maybe indeed what it makes sense, and maybe it's defined. I don't know the literature so well. Is there something which is called J covariant spectrum? I mean, it comes down to this actually. So if I mean, I do think that if you put Z or even some cyclic group action, the splitting becomes a problem. Therefore, emulsification becomes a problem, and there is new theory there. But I don't know if this has been studied. But I mean, if it has been, then indeed there will be new invariants coming from this J covariant spectrum. But I can't believe, I mean, especially Dima, I mean, Arnold, with the all tons of students that were written most, that didn't pose this question. So I haven't looked.
it did for C2.
For Z2, they've done. I
Because
see.
that also acts on the modes.
I see.
But otherwise, it's
Okay. I mean, if this can be done, and I think probably for cyclic groups can be, I mean, this will give new abstractions to rationality. Yeah.
Go back a few slides, go back to the definition of the new atom percent group. Okay, yes. I have some questions here. So, like, for choose the symbols, like, what's the, how could you choose a G prime and G double prime? Like,
Well, so these are the, I mean, the group has a subgroup and so on. I mean, so there are some subvarieties which are fixed by the whole group, but then the subgroups act non-trivially on them, and so that's what this whole. I mean, so if you define the symbols, these things matter. And so that's the,
Okay, so and then the next thing is the row from G prime. Try to record the G prime actions on the or non-bundle.
yeah, it's all just a classical definition of a symbol.
Okay, sure. And the last thing S in the D to the so what's the last piece? That's S, capital S that belongs to the Z, which is 0 to the power C prime, G prime, double prime over G prime. That's 0.
I mean, so I should have spelled this out. So this is additionally, so this is an additional restriction on the characters that we want to use. I mean, but, so I mean, in order to explain it, I should have written more details. But it's once again, it's really copied from Chinkel-Peston paper, which you know very well. I mean, maybe it's some interpretation to make it possible to apply to atoms theory, but it's the same.
Your invariant delta, you said the connection with the minimal exponent in the spectrum. But you also mentioned that is motivated by asymptotics of the solutions of
Yes,
the quantum.
yes. So I mean,
are the asymptotics of the solution of the quantum number related to the spectrum?
yes, I gave you a formula. So I mean, which you can. So if you are good with Sage, you can actually do it right now. So write the solutions of this differential equation for the k. And so what you are going to get as an asymptotic is that this u is equal to so it's about this so some exponents here, and you have this sub-exponential growth there. So growth here, and you have u in power minus 5/6 in this case. This is for the cubic. And so as I told you, delta, so this is the smallest, and then other is a little bit bigger. So you have the delta is equal to, so you know this by delta 1 minus 2 times delta 1. There are formulas for all of them. And so in this case, you get 5/3, which shows exactly this thing what gives you the abstraction solution. So this is delta 1. This is the lowest asymptotic.
There are no other questions. Let's thank Ludmil, and we meet again at 11:30.
All right.